Section: Introduction. In this section, we introduce Direct Preference Optimization, DPO, as a simpler alternative to reinforcement learning from human feedback, RLHF, for large language models, LLMs. DPO avoids the complexity of learning a reward model from human preferences, making it easier to implement and train compared to RLHF methods. After training, DPO implicitly defines a reward model for responses to prompts. This reward can be mathematically expressed in terms of optimal and reference policies, with a parameter beta and a normalizing constant z. We investigate whether the implicit reward model obtained from DPO training can enhance the language model alignment with human preferences. Our method, called DICE, self-alignment with DPO implicit rewards, leverages these implicit rewards in a bootstrapping fashion to iteratively improve the LLM. We address issues such as length exploitation and over-reliance on the implicit reward model by incorporating length-regularized reward shaping and replaying high-quality human preference data. DICE significantly enhances LLM alignment with various base models, outperforming Gemini Pro with only 8B parameters and without requiring additional data or reward models. Our contributions include utilizing the readily available implicit reward model in a DPO-trained LLM, introducing length-regularized reward shaping and experience replay techniques, and demonstrating substantial improvements in alignment with different base models. In contrast to previous work on self-improving fine-tuning and on policy sampling in preference tuning, our focus is on enhancing a DPO-trained model through bootstrapping with its implicit rewards. We aim to improve the policy model using preference data closer to on-policy samples, leading to enhanced performance and efficiency. Our approach builds on the observation that DPO-ed models implicitly define dense reward functions at the token level, which we leverage for self-alignment and model improvement. Section Summary. In this section, we introduce Direct Preference Optimization, DPO, as a simpler alternative to reinforcement learning from human feedback, RLHF, for large language models, LLMs. DPO implicitly specifies a reward model, making it easier to implement and train compared to RLHF. By utilizing the readily available implicit reward model in a DPO-ed LLM, our proposed approach, DICE, significantly improves alignment with human preferences and achieves better performance than existing models with fewer parameters and without the need for external feedback or reward models. Section: Preliminaries. In this section, we will provide a simplified explanation of the standard RLHF and DPO algorithms. We will discuss how DPO creates an implicit reward model and its use in our work. In preference tuning, each input, X, is paired with two possible responses, Y_1 and Y_2. A human or AI annotator gives feedback O, Y_1 suck, Y_2 vert X, in 0, 1, to show which response is preferred. The preferred response is labeled as Y_W, and the other as Y_L. It is assumed that human preferences follow the Bradley-Terry model. We can train a reward model R_phi, X, Y, using maximum likelihood, where sigma is the logistic function. The RLHF algorithm treats the language model as a policy and optimizes it using the reward model R_phi. The optimization objective balances maximizing the reward R_phi, X, Y, and staying close to a reference distribution. The DPO algorithm also starts with a similar objective as RLHF but finds a direct relation between the reward and the optimal policy. This relation allows for training the optimal model directly on feedback data without the need for on-policy sampling or extensive tuning. DPO simplifies the training process but may result in an inferior policy if trained solely on a fixed dataset. To address this, we propose an iterative training framework called DICE, which combines length-regularized implicit rewards with experience replay to improve performance and prevent forgetting previous learning. Section Summary. In this section, we provide a concise overview of the standard RLHF and DPO algorithms, highlighting the implicit reward model induced by DPO. Preference tuning involves pairwise preferences where each prompt is paired with two responses, and human or AI annotators provide feedback on preferences. DPO simplifies language model alignment by deriving a closed-form relation between reward and optimal policy, enabling direct training on feedback data without the need for extensive hyperparameter tuning. Section: Iterative DPO with on-policy sampling. In this section, we utilize the iterative DPO preference tuning framework. We begin with a base language model, which is adjusted using DPO from an initial reference model, typically an SFT model. In each round, we gather on-policy responses from the current policy given a prompt. The responses with the highest and lowest implicit rewards are labeled as winning and losing responses, creating a new preference dataset. The policy is then fine-tuned with DPO's objective to update it, and this process is repeated to enhance the language model iteratively. To explore the impact of on-policy sampling, we introduce a general notation for the sampling policy at each round and compare on-policy sampling with sampling from an offline dataset. For a given prompt, we identify the optimal response and suboptimal ones. The preferences sampled from the policy at each round are denoted accordingly. By analyzing the DPO loss at each round and the logistic function, we can minimize the loss by focusing on reducing the likelihood of the lowest rated response without considering the likelihood of other suboptimal responses. After several rounds of optimization, we are interested in the likelihood of producing the optimal response. The analysis reveals the limitations of training on a fixed offline dataset. On-policy sampling helps address the issue of suboptimal responses not being sampled and optimized, leading to improved convergence towards the optimal policy. This approach gradually enhances the language model policy over rounds. Section Summary. In this section, we utilize an iterative DPO preference tuning framework to enhance a base language model by sampling on-policy responses and constructing preference datasets. By comparing on-policy sampling with offline dataset sampling, we show that on-policy sampling helps optimize suboptimal responses, leading to improved convergence towards the optimal policy. This iterative process gradually enhances the language model policy, addressing deficiencies in training on fixed offline datasets. Section: Length Regularized Implicit Rewards. In this section, we discuss the issue of length bias in preference tuning and how it can affect the responses generated by language models. We acknowledge that human annotators tend to prefer longer responses, leading to a bias towards verbosity in the collected preference labels. This bias is exacerbated by iterative self-alignment processes, where longer and preferred responses are reinforced, causing the language model to generate even lengthier outputs over time. The vanilla DPO implicit rewards also exhibit length bias when creating preference datasets. We illustrate this bias by comparing the distribution of string length differences between winning and losing responses. The vanilla implicit rewards result in a skewed distribution with an average length difference of 1031, while a high-quality preference dataset shows a more normally distributed length difference. To address this length exploitation issue, we introduce a length regularized (LR) reward shaping term in the implicit reward function. This term penalizes the length of the response to shape the reward accordingly. By adjusting the penalty strength parameter, we can construct different versions of the preference dataset, aiming to minimize the average absolute difference in response length and create a more balanced dataset. We optimize the penalty strength parameter using a black box optimizer to achieve an approximately unbiased dataset. A simple random search method proves effective in transforming the dataset into a more evenly distributed one. The optimized dataset, denoted as D, alpha-star, is then used for the next round of DPO training. Details of the optimization process can be found in the appendix. It is important to note that our approach differs from methods that incorporate token length as a regularizer during training. Our reward shaping occurs during dataset construction, eliminating the need for costly hyperparameter tuning. Section Summary. In this section, we address the issue of length bias in preference tuning, which can lead to longer responses being favored in language models. To mitigate this bias, we introduce a length regularized reward shaping term that penalizes response length during dataset construction. By optimizing this term, we create a more evenly distributed preference dataset, reducing length exploitation without the need for extensive hyperparameter tuning. Section: Experiments. In this section, we empirically explore DICE. Our discoveries emphasize several important points. 1. DICE notably enhances model performance on the widely used AlpacaEval 2.0 leaderboard, boosting the length-controlled win rate by up to 9.35%. 2. Our top model, derived from an 8B base model, Llama 3 to 8B DPO, outperforms Gemini Pro without any extra human annotations or external reward model, solely relying on the preference dataset used in the initial DPO training of the base model. 3. The two proposed techniques in sections LC_RS and EXPR are crucial for DICE. For the experiment setup, we use Llama 3 to 8B DPO and Zephyr 7B Beta as our base models, trained following the Zephyr pipeline. We utilize the Ultra Feedback Preference dataset and randomly select around 10K preference pairs as the offline dataset D_offline. Our goal is to demonstrate the language model's improvement from a DPO ed model and a subset of the preference dataset used in the initial DPO training. To generate responses and construct the dataset, we sample responses from the current policy at the start of each round with specific settings. We then reward each prompt response pair using implicit and length regularized reward models to create the Debias dataset D, alpha_star. This dataset combines D, alpha_star, with D_offline. In terms of training, we conduct all experiments on 8 NVIDIA A100 GPUs. For DICE, we train 2 rounds in total, each for 300 steps on a preference dataset with 9.6K preference pairs. The global training batch size is 32, and we use a specific learning rate with a constant schedule and warm-up steps. We fine-tune beta for each method and report their best performance. Additionally, we hypertune the experience replay ratio gamma for our approach. We evaluate our method using AlpacaEval 2.0, an LLM-based automatic evaluation benchmark. The results show that DICE significantly enhances a DPO ed model, outperforming other baselines and the base model in both Zephyr and Llama 3 settings. DICE Llama 3 8B even surpasses the official Instruct version of Llama 3 by 4.63% on the public leaderboard and outperforms Gemini Pro without requiring additional data or external reward models. Section Summary. In this section, we empirically investigate DICE and highlight key findings. DICE significantly enhances model performance on AlpacaEval 2.0, improving the length-controlled win rate by up to 9.35%. Our best model, Llama 3 to 8B DPO, outperforms Gemini Pro without additional human annotations, relying solely on the preference dataset used in the initial DPO training. The experiments emphasize the importance of specific techniques within DICE for optimal performance. Section: DICE is compatible with other direct alignment from preference algorithms. In this section, we explore how DICE can work alongside other direct alignment from preference (DAP) algorithms. While DICE is most effective with DPO due to its support for iterative training, we want to see if the dataset produced by DICE can also enhance the base model with other DAP algorithms. In our experiments in the Zephyr setting, we fine-tune the policy model using the dataset generated by DICE with KTO, IPO, and hinge loss. The training process follows the setup protocol described earlier. The results indicate that all DAP algorithms benefit from the new data generated by the current policy and DPO implicit reward model with LR reward shaping, showing higher LC win rates than offline DPO. Notably, DICE performs best with DPO, followed by IPO. However, Dice IPO faces a significant length exploitation issue even with LR reward shaping applied to the dataset. We then delve into an ablation study to examine the impact of LR reward shaping and experience replay. LR reward shaping penalizes verbose responses and helps create a Debias dataset using an optimal penalty strength. By conducting experiments with different mixture ratios and ablation of design choices, we observe that no LR reward shaping leads to length exploitation issues. On the other hand, a slightly larger penalty strength can mitigate length exploitation but may affect response quality. Our proposed method of determining the optimal penalty strength yields the best performance. Regarding experience replay, it results in a mixed dataset combining offline and generated data. Through experiments with varying gamma values, we find that a gamma of 0.5 offers the best performance, striking a balance between off-policy samples and reinforcing the current policy. This approach prevents catastrophic forgetting and optimizes the policy effectively. We acknowledge some limitations in our work, such as the reliance on well-trained implicit reward models and the challenge of continuous improvement over iterations. Future research could explore the rewarding capabilities of different DPO variants and develop methods for continuous policy model enhancement. It is essential to address potential misuse of our method for generating harmful content by establishing safeguards and ethical guidelines.